Okay, this video is on chapter 3, which is about vectors. Section 3.1 deals with coordinate systems. In particular, we're going to look at rectangular and polar systems and how you move between the two. Rectangular, you might hear called Cartesian. So a rectangular coordinate system, that's what we have as our typical x, y, and a point is defined by an ordered pair of x, y. And in polar, we usually draw it the same way, but that point will be described by some r and theta value, meaning you rotate from what would be the positive x-axis, some angle theta, and then you go a distance from the origin r. So let's talk about reaching point over here. You could either go over x1 and up y1, or you could go up y1 and over x1. And in polar coordinates, you would go sweep out an angle theta and then go a distance r. All right, section 3.1 goes on to talk about the way to convert here. If we're in rectangular and we want to go to polar, we're going to take our x, y, and r then is equal to the square root of x squared, the coordinate for x squared, and the coordinate of y squared, and then square root. And that's just our distance formula, right? And if we want to find theta, theta is given to be the inverse tangent of y over x. All right, if we're going to convert from polar to rectangular, then we're given some r theta, then x is going to be r cosine theta, and y is going to be r sine theta. I will say, to be careful here, to make sure that you're in the right quadrant, right? So note the quadrant here, which for sine and cosine, in your calculator, it only gives you 2 quadrants, right? Cosine gives you an answer either in the, let's see, 4th or 1st quadrant, and sine gives you an answer in the 1st or 2nd quadrant. So if you were in one of the other quadrants, you would need to pay attention. Actually, for this direction, that's okay. It's the other direction on your tangent. So let me extend that to include this also. Yeah. And that's why I don't like to stick to this definition, okay? In general, in physics, we prefer triangle tree. which means I'm not going to worry about which direction it's pointing or anything. Just if I have a vector here, instead of describing it in terms of this angle theta and this distance r, I'm just going to approach it with a rectangle or a triangle made to the coordinate axis with sides parallel to the coordinate axis. And I know that this is going to be the x component of r, and this is going to be the y component of r. And if this theta here, we're going to take theta minus 180 to give us our angle. Why did we do that? Because we have 180 degrees of rotation here that we're taking out. So if we were given, 210 degrees or 245 degrees, whatever, we would subtract that to get this angle. Now, so since we actually want the angle interior here, let's not do it this way. What we're going to do instead is we're going to take 270 minus theta, right? That's what makes more sense in this case. All right. Anyway, we want to find the reference angle that we need to use for our triangle. In general, when you're doing a physics problem, you probably know the reference angle and you don't know what the angle in standard position is. And that's why we tend to not stick to using standard position. All right, with this approach, we follow the SOHCAHTOA mnemonic, which says that the sine of angle theta is equal to the opposite over the hypotenuse. Cosine of angle theta is equal to the adjacent length over the hypotenuse length. And the tangent is the opposite length over the adjacent length. All right, so what that means for our example here, if I wanted to, let me just draw it again on the next page. Wanted to, for example, find the length of Rx and Ry for this angle. I'm going to call it phi since I called theta something different earlier. So if I, example, wanted to find Rx, how would I do that? Well, if I look at the angle phi, Rx is the opposite. So I'm going to use the sine because that's the one that has the opposite. So I'm going to use that the sine of phi is equal to the opposite side over the hypotenuse. And it's important to note here the magnitude of the vector is always the length of the hypotenuse. All right, so if you draw your triangle in such a way that the hypotenuse is not the vector length, then you've drawn your sides not parallel to your coordinate axes, most likely. All right, so if we wanted to find Rx, then we would just multiply by R and we would have R sine phi. Similarly, we would do the same thing for Ry. Right, so it's the adjacent, so cosine phi is Ry over R. And you get that Ry is R cosine phi. So once you've done a lot of vectors and finding components, you're going to get comfortable where the adjacent side is the magnitude times the cosine of the angle. The opposite side is the magnitude times the sine of the angle. That just takes familiarity dealing with vectors. And again, if you have your components then I think we'll stop with that there, and that brings us up to section 3.2 and 3.3. The next thing I want to talk about would be covered under 3.3. So let's go ahead and finish 3.2 in this video, and then we'll move on. So this is about scalar quantities and vector quantities. If you've watched some of the other videos, we've talked about this already in some parts. So a scalar is just a number with units, right? Some quantity. A vector is a number with units and a direction. All right, so what are we talking about here? If I talk about a distance, I can say that I am 14 feet from the door. But if I say that I am 14 feet, 17 degrees north of the door, right? Then that is a displacement, right? I've now told you what direction from my reference point I am. I'm not just giving you the length of how far it is. Similarly, related things, we have speed and velocity. So these are related quantities. All right. Some unrelated quantities, you have things like temperature. I can't say that it's, 100 degrees in some direction. That doesn't make sense, right? That is an innate scalar quantity. Energy also doesn't have direction. That is a innate scalar quantity. Momentum is a vector quantity because it definitely has a direction. When we think about momentum, even in colloquial terms, it's motion in a direction, right? So I don't think there's anything else I want to say about scalar versus vector quantities. The main thing here is specific instances when we use these that you want to get used to.